A three-phase load is connected to a three-phased balanced supply as shown in the figure. If VAN is 100 at an angle 0, VBN is 100 at an angle 120, VCN is equals to 100 at an angle minus 240, where angles are considered positive in anti-clockwise direction, and the value of R for zero current in the neutral wire is. Okay. So here he's telling that for the neutral current to be zero, what should be the value of the resistor R? He has given the impedance values in other two phases. My first question is in this question is whether the given system, three-phase system, is balanced or not. Anyone?
Balanced.
Whether the given three-phase system is balanced or not. It's telling that the neutral current is zero, but whether the given system is balanced or not. Anybody who thinks that it is unbalanced? It is absolutely unbalanced system. It is absolutely unbalanced system. See, again, I'm telling you, ma, for a balanced system, there are two conditions that must be satisfied. The first thing is magnitude of current IA, IB, IC should be same, and your neutral current, that is the phasor sum or time domain sum of three currents, should be zero. Okay, he's telling that the neutral current is zero, but you don't know whether the magnitude of the three currents IA, IB, IC are same or not. However, if you see the load, in one phase the load is a resistor, the other phase it is inductor, another phase it is capacitor. The loads are unbalanced. So if any one of the impedance parameter is different in all three phases, then the system is unbalanced, because the current won't be balanced. The impedances in all three phases should be same. Here they clearly it shows that it is an unbalanced system because the impedances in A phase, B phase and C phase are different. So it is absolutely unbalanced three-phase system. But however, even in this case, the neutral current somehow has become zero. So for this neutral current to be zero, what is the value of resistor that we need to compute? Okay, understand? It is an unbalanced system. Now, what is the value of IA? Tell me, what is the value of IA? The current IA is given by VAN divided by R, whose value is 100 at an angle 0 divided by R. Okay. What is the current IB? VBN divided by what is the impedance in B phase? It is J10. So 100 at an angle minus 120 degrees divided by J10. What is IC? VCN divided by what is impedance in C phase? Minus J10, whose value is 100 at an angle minus 240. I can write it as plus 120 divided by minus J10. Okay. How these currents are there? These currents are such that the sum of these three currents, the neutral current is what? Neutral current is sum of I phase current, B phase current and C phase current. Okay, your neutral current IN is sum of IA, IB and IC. I have applied KCL at this point. So IN, that is equals to 0, that is equals to 100 at an angle 0 by R plus 100 at an angle minus 120 divided by J10 plus 100 at an angle plus 120 degrees divided by minus J10. Okay. So, which implies minus 100 by R. 100 at an angle 0 is nothing but 100. 100 by R is equals to, what is the magnitude of this second term? Magnitude is 10. This J is nothing but 1 at an angle 90. J is nothing but 1 at an angle 90. When it goes to the numerator, it will become minus J, which is equals to 1 at an angle minus 90 degrees. So this value will become 100, 10 at an angle minus 120 minus 90. The third term will become 10 because 100 divided by 10 is 10. So minus J, when it goes to the numerator, it will become 120 plus 90. So minus 100 by R is equals to 10 at an angle minus 210 plus 10 at an angle plus 210. Try to solve it. How we can write 10 cos of minus 210 plus J into 10 sine of minus 210 plus 10 cos 210 plus J into 10 sine 210. Okay, this and this will automatically cancel each other because one is a negative. Sine of minus theta is minus sine theta, so you can directly cancel them. So minus 100 by R is equals to cos 210. We can write 2 into 10 into cos 210. Why, sir? Cos of minus theta is cos theta. So this will become how much, which implies minus 100 by R is equals to 20. Cos 180 plus theta is minus cos theta, minus 20 into cos 30. Cos 30 is how much? Root 3 by 2. So this will become minus 10. So which implies R is equals to 100 by 10 root 3. Calculate this value and tell. See, one thing I'm telling you, if you're good at numbers, always any competitive exam will not test your calculator skills. Any problem which they're giving, you will be able to solve with hand if you're good at this trigonometry and complex algebra. Anybody tell me the value of 100 divided by this one? This is 10 divided by root 3. What is the value? 5.77 ohm. Okay. So this is the resistive value for which you are going to get the zero neutral current. Did you follow the question? Actually, why it has become zero, I'll explain you. Just try listen it. If you understand, well and good. Otherwise, it's also okay. This is my VA. VB and VC. The three voltages that are balanced. 100 at an angle 0. No, let me write it. Okay. Now, what is the load that is connected in B phase? Inductor. What is connected in B phase? Inductor. When you connect inductor across B phase, the B phase current lags the B phase voltage by 90 degrees, because in inductor current lags the voltage by 90 degrees. So your inductive current will be like this, IB. The angle here would be 90 degrees. Understand? Similarly, what you have connected in C phase? A capacitor. You have connected a capacitor. So when you connect a capacitor, the current through the capacitor leads the respective voltage by how much? 90 degrees. So your current IC, your current IC will lead VC by 90 degrees. Magnitude wise, IB and IC are same because their magnitude of impedance is 10 ohm only. Now, if you add these two currents, if you add these two currents, the resultant is, this is the resultant current. This is IB plus IC. Okay. Now, if resistor is connected in A phase, then the current, how it would be? This current would be in phase with the voltage. Okay. Here what is happening? The current IA is exactly in phase opposition with the current IB plus IC. That's what happening because of that such type of connection. So now, if the magnitude of phase A current, if it exactly matches with the magnitude of IB plus IC, what's happening? Since they are 180 degrees out of phase, the sum IA plus the phasor sum of IA plus IB plus IC is becoming zero. Is becoming zero. Understand? That's why the neutral current have become zero. Okay. You interchange the inductive impedance in C phase and capacitive impedance in B phase. Again, you try to do the same problem. In that case, the neutral current will become, just you can practice if you're interested. If we interchange J10 and minus J10, then neutral current will become, neutral current will become 2 times 2 times 100 divided by 5.77 ampere. Purely resistive current will flow in the neutral. You can try to solve this as a homework. I'm giving a hint. If we interchange the minus J10, J10 and minus J10, then your neutral current will become this value. They have asked this question. They may ask that question also in near future. Okay. Next topic is transmission lines. So the most commonly used conductor materials for transmission conductors are copper and aluminum. Even though the best conductor is silver and gold, since we cannot afford them, we'll go for the next best and affordable conductors, which are copper and aluminum. Okay. See, when I say transmission line, any conductor that carries electrical energy is a transmission conductor. Even the small cable or a small wire that is connecting from your switchboard to fan is also a transmission line, but it's very short. Okay. So any conductor which carries electrical energy from one point to another point is classified as a transmission line. Okay. So mostly what you see for indoor applications, we use copper. For outdoor and overhead applications, we go for aluminum. So we'll just try to compare and learn few points about these two common type of conductor materials, that is copper and aluminum. Copper and aluminum. Copper has more conductivity than aluminum. Conductivity sigma. The density of copper is more, and copper will corrode when it is exposed to moisture and oxygen. It corrodes. Copper is costly. The tensile strength of copper is more. But when you come to aluminum, conductivity is less. Density is what? What is density? Mass by volume. So density of copper is more. That's why its tensile strength is more. So for the same volume, your mass is very less. Uh, for the same volume, the mass is more, where the density is high. Okay. And aluminum does not corrode. Aluminum is cheaper when compared to the copper, and the tensile strength is light. So when you come to overhead transmission conductors, when you come to overhead transmission conductors, aluminum is the unanimous choice. Aluminum is the unanimous choice. Why? Because all these points are advantages only. There is no disadvantage. Aluminum is cheap. Aluminum does not corrode. The tensile strength, the mechanical strength of that aluminum is less. Even that is an advantage. How? We'll discuss. Density is less. That means for 1 kg of aluminum, you will get more volume of aluminum when compared to the copper. Okay. Next, conductivity is less. It is also advantage. Why it is advantage? Will come across. So for overhead transmission lines, the all over the world, the obvious material that we use for power transmission is aluminum, because it has all the advantages. All these are the advantages for aluminum. Okay. So what do you mean by conductivity? Suppose this is a copper conductor which can carry 100 amperes current. Okay. So in order to carry the same 100 ampere, the size of aluminum required is more. Size of the conductor required for aluminum will be more to carry same 100 ampere. Size is less, whereas here the size required is more. Okay, understand. So bigger size conductors, they will reduce the inductance, and as well as they help in the reducing the corona effect. So we'll discuss all those little later. So having less conductivity will increase the size of conductor for the same current carrying capacity, which is also advantages, which is also having its own advantages in the overhead transmission. Okay. Any doubts here so far? Can I move forward? The next point is advantages of high voltage transmission. Okay. First, before going to that, if capital R is resistance of a transmission conductor, then total real power loss in three-phase transmission is given by 3 into I square into R. So if R is the resistance of a transmission conductor, then the total real power loss in the three-phase transmission line is 3 times I square R. 3 times I square R, so many watts. Okay. This is one point. The second point is the MVA rating or the apparent power rating of transmission line is root 3 VTI or root 3 VLIL, where VL is the transmission voltage in kilovolt, which is an RMS value, and IL is the current carrying capacity of transmission line. That means how much current it can safely carry without getting damaged. Whereas VL is the transmission line voltage, like 33 kV, 66 kV, like that. So how much power that we can transfer, apparent power that we can transfer in a transmission line is given by root 3 VLIL. Okay. So transmission line capacity is root 3 VLIL. Understand? Now, which implies current capacity of a transmission line is given by line capacity divided by root 3 into transmission voltage into transmission voltage. Okay. Third point, in a transmission line, always receiving end line to line voltage is specified. Sir, what is the meaning of this point? When I say 33 kV transmission line, someone asks, sir, whether this 33 kV is sending end voltage or receiving end voltage or between the voltage. No, we always specify the transmission line voltage at the receiving end. So even though the both values will be more or less same, when I say 33 kV transmission line, the receiving end voltage is 33 kV, the sending end voltage will be somewhere 2 or 300 volt more than that. Okay, but to be very precise, what voltage we specify in a transmission line, we specify the receiving end line to line voltage of a transmission line. Understand? So these 3 points you have to remember regarding the transmission line. Now we go for the advantages of the high voltage transmission. Suppose the power carried by the transmission line is given by the complex power carried by the transmission line is root 3 or 3 root 3 VL IL conjugate. Suddenly he asked, sir, why you have not kept conjugate here? Why you have kept conjugate here? So when you want the power, complex power in terms of magnitude, it is called apparent power. It is called apparent power. So that means, for example, I can write the complex power of a load absorbed by a load as 100 MVA, which is a magnitude. I can also write the complex power absorbed by load as 80 megawatt plus J 60 MVAR. Okay, that means if I write the complex power in P plus JQ form in a rectangular form, it is called complex power. When I write take the only magnitude of that one, it is called apparent power. It is called apparent power. That is the only difference. Okay, if you take the magnitude of this S load, what are you going to get? Square root of 80 square plus 60 square, which is 100 MVA. Understand? So if you only consider the magnitude of complex power, it is termed as apparent power, whose unit is volt ampere. When you specify the complex power as real power plus J into complex power, then it is called a complex power and apparent power. Likewise, the terms are used. So the complex power transferred in a line is given by root 3 VLIL conjugate. So now if I want IL square or IL, it will become S line divided by root 3 into VL, root 3 into VL whole conjugate. Now IL square into R into 3 is the power loss in the transmission line, which I can write it as, first let us write IL square. IL square will become S line square by 3 into VL square. So real power loss in the transmission line is given by 3 IL square into R, which is equals to 3 into S line square by 3 into V line square into R. So, which implies power loss in a transmission line is inversely proportional to 1 by VL square, or power loss is inversely proportional to 1 by transmission voltage square. So if you go for higher and higher voltage transmissions, the real power losses in the transmission line are reduced. By what factor if you reduced? Remember, this is the power loss in the transmission line. If you double the transmission voltage, your transmission losses are reduced by 1/4. They are reduced by 1/4 because real power loss in the transmission line is directly proportional to 1 by the transmission voltage square. 1 by transmission voltage square. That is high voltage transmission reduces power loss in the transmission line. By what factor? That we have discussed. If you increase the transmission voltage by 2 times, your real power losses are reduced by 1 by 4th time. They become 1/4 of the previous losses. Okay. Is this point clear, ma? Okay. So similarly, from the same relationship, I can write current through the transmission line is given by S line divided by root 3 into V line. Okay. So for same complex power, complex for the same power transfer capacity of the transmission line, the current through the transmission line is inversely proportional to the voltage of transmission. You can clearly see that the current flowing through the transmission line is inversely proportional to the transmission line voltage. Okay, so by increasing the transmission voltage, the transmission current is reduced. So once the transmission current is reduced, what happens? The size of the transmission conductor reduces. The area of cross section of the transmission conductor reduces, which in turn leads to saving of the conductor material. Okay, so high voltage transmission reduces transmission current, thus the size and material required, thus the material required for conductor is reduced. Okay, here this is important for same power transfer capacity. That means S line is constant. That means S line is constant here. S line is constant. Okay, this is the second advantage. The third and most important advantage is that the power transferred to the load is given by PL square by ZL conjugate, where we know that VL is the receiving and line to line voltage vector. I can write it as transmission voltage square divided by ZL conjugate. Okay, so for a fixed value of ZL, the complex power transferred to the load is directly proportional to square of transmission voltage. Square of transmission voltage. That means with, what is the point? With high voltage transmission, we can transfer more power to the load. Same. Mainly, we'll study in the coming classes. Transmission lines are mainly used to transfer real power. The reactive power part is taken care by the local capacitors and local compensators. So mainly in transmission line, we try to transfer real power because generator is the only element that generates the active power, whereas the reactive power can be generated locally by some other elements. So the same sentence we can directly write it as the real power transferred to the load is directly proportional to the square of transmission voltage. Real power transmitted to the load is directly proportional to square of transmission voltage. So higher is the transmission voltage, more is the power that we can transfer to the load. So that is one more advantage of the high voltage transmission. Don't get confused between this point and the first point. Here we are speaking about the transmission losses. P loss means what? Transmission losses. Okay, which are inversely proportional to 1 by transmission voltage square. Whereas here this is the active or real power transferred to the load, which is directly proportional to the square of transmission voltage. Okay, so for the same load ZL impedance, if double the transmission voltage, then we can transfer 4 times more power than the previous case. Okay, these are the main advantages of the high voltage transmission. One more advantage is that once the transmission current reduces, then voltage drop in the transmission line. What is the voltage drop in the transmission line? I line into Z line. The voltage drop in the transmission line also reduces. Understand? Once the current flowing through the transmission line reduces, then voltage drop in the transmission line also reduces, which gives better voltage regulation. Better voltage regulation. Understand? So what is the ideal voltage regulation? Best voltage regulation is zero, where sending end voltage and receiving end voltage are same. There is no drop in between. That is called best voltage regulation. So lesser is the drop in the transmission line, better is the voltage regulation. This is one more advantage we'll get by using the high voltage transmission lines. So have you understood all four advantages, ma?
Excuse me, sir, I have a doubt.
Yes, ma'am.
Sir, means in high voltage case, told like as current means as the current reduces, the size can be reduced, right?
For the
That is
same power capacity. Yes, yes.
for the same power capacity. But while
Okay.
explaining that copper and aluminum, we were telling like as conductivity is less, the size is more for aluminum, and that is an advantage.
Yes, ma.
What is that? Means one place we are telling like the size is more, it's an advantage, and the other case the size is less, it's an advantage.
Okay. See, when you analyze in the context of the volume of the material that is required, okay. So suppose, just for a layman's example, if your end power required for a load is say 1 kilowatt, here you require a power of 1 kilowatt. Okay. Now the voltage at which I am supplying it is say 50 volts. So in order to transfer 1 kilowatt, what should be the current in this case? 20 ampere, because 15 to 20 will give me how much? 1 kilowatt. But if I keep my voltage as say 100 volt, how much current is required to transfer the same power? 10 ampere. So here, in order to send 10 ampere current, my cross section of the copper wire should be, my cross section of the conductor will be lesser. In order to design it to carry 20 ampere, my size of conductor or the cross section of the conductor will be more. Understand? So when I go for higher and higher voltage of transmission, in order to transfer same power to the transmission line, my transmission current reduces. Understand? With which the volume of the material that is required to commission a transmission line reduces. Yes or no?
Yes.
Okay, this is an advantage. But at very high voltage transmission that we'll discuss in Corona, where we increase the size of conductor intentionally, not by wasting the conductor material. We use some other techniques there that you'll learn into most probably next class, where by increasing the overall size of the conductor by using some garbage material or by interconnecting the other conductors, the electric field intensity that is surrounding the conductor we will reduce. So once we reduce the electric field intensity surrounding the conductor, then we can reduce something called as corona effect. We can reduce. Okay. When we are going for purchasing aluminum, by default we are getting a more cross section area for the conductor, more cross section area for the conductor. With the more size of the conductor, even though some one disadvantage is existing that we are using more conductor material, but since its density is less, the weight of the conductor will be less. However, in order to carry same current, the overall size increases. So when overall size increases, it also offers certain advantages, I mean to say. Okay. So in your terms, increasing size in this context is a disadvantage. But in context of corona, it is an advantage. Understand? So every advantage, there is nothing having only advantages. It will have some disadvantages also. Okay. I don't know how far I am able to clear your doubt. In the context of volume of material, it is a disadvantage. In the context of reduced electric field intensity, it is a advantage. Okay.
Okay, sir. It's clear. Thank you, sir.
Thank you. We'll understand gradually. Okay, right. Any other doubts? Shall we move to next topic? Any other doubts you can ask me. Clear? Okay. Now we'll see what is the disadvantages of high voltage. I said no, nothing has advantages only. Every coin has the other side. Tell me what are the disadvantages? High voltage transmission. Anyone? Cost
Control.
of insulation, cost of switchgear, cost of transformers, cost of towers, and cost of ROW. All costs will increase. Why? For more is the voltage, we have to provide more insulation. Insulation is provided between the ground potential point and the conductor. Ground potential point and the conductor. So for example, in a transmission line, I'll say, just give me. Now, this is a transmission tower. This one is called cross arm. Cross arm. Now, what is the where the tower is landing on the ground? So, what is the potential of ground? 0 volt. Okay. What is the potential of the tower? 0 volt. What is the potential of cross arm? 0 volt. So, till this point, the voltage is 0. Now, what is the voltage at this point? Or what is the voltage difference between these 2 points? Anyone? It is the phase to neutral voltage. It is the phase to neutral voltage. Okay, so suppose our transmission line voltage is 66 kV. So you have to provide insulation for which voltage? So the phase to neutral voltage will become 66 kV divided by root 3, because always the transmission voltage is mentioned in line to line RMS voltage. So our phase to neutral voltage is 66 by root 3. Now I will take a factor of safety of 5. So my design insulation voltage will become 66 by root 3 into 5. For this much voltage, I have to design the insulation. So this one. So if you go for higher and higher voltage transmission, my cost of insulation will increase because I have to provide more insulation. Okay, I have to provide more insulation. That is one thing. And this point from the from the conductor position to the earth, this is called ground clearance. Ground clearance. So as the transmission voltage increases, suppose if you k 11 kV pole which you see in your streets, the minimum ground clearance required is say some 6 meters. But whereas for 33 kV line, it will become 11 meters. For 66 kV line, it will become 20 meters. Like that, for higher and higher voltage transmission, I have to provide more ground clearance. I have to provide more ground clearance. In order to provide more ground clearance, my size of the tower and cost of tower will increase. My size of tower and cost of tower will increase. Okay. And the third point is switchgear. So a breaker that closes 33 kV or a breaker that closes 132 kV or a breaker that closes 400 kV, the design cost operation will be different. So the cost of cost of circuit breakers will drastically increase with the increase of the voltage. For small voltages, what you use is single pole MCB to make and break. For 415 volts also you can use 3 pole MCB, miniature circuit breakers. But when you go for high voltages, say 1000 voltage, you require 8 circuit breaker because the arc quenching mechanism, the heat dissipation mechanism should be break lever. For from 3.3 kV to 66 kV, you can go for vacuum circuit breakers. Above that, you have to go for the SF6 or air blast circuit breakers. So the technology, the methodology, and the cost of circuit breakers will also vary from low voltage to high voltage, which that is called switchgear cost. Even switchgear costs include circuit breakers, CTs, current transformers, and potential transformers. All their costs will increase. Transformers. We know that we cannot generate high voltage. The maximum generation is possible is mainly people will generate at 11 kV. Some places they generate uh, 15 kV, some places they generate 22 or 23 kV. Maximum highest generation in India is around 23 kV in Kudankulam nuclear power plant. In world, it is only 30 kV because we cannot generate the power at high voltages because of the size of the stator increases drastically high and the cost also increases drastically. So in order to step up these small voltages to very high voltages, we require a high voltage transformers, so which will, and even to step down from very high voltages to intermediate voltages, the cost of transformers also will increase. Okay, so the fourth is right of way. Right of way. Why? Suppose in your house you're having a lot of corridor, a lot of empty space in the backyard. If the transmission company comes and tells you, can I place my 132 kV transmission tower in your corridor of your house? Will you give permission? Will you give permission? You're having empty space, and that too, you're an electrical engineer. The transmission company, Kerala State Electricity Board, has come and requested you, gentlemen, can you please give me some place where I can station my 132 kV transmission tower? Will you give the permission? You won't. there is a risk involved in it. There will be some magnetic and electric fields. You always have a fear that you enter into that and you may get electrocuted. Understand? So the second option, what they'll give every month I'll pay you 1 lakh rupee. Can you please allow me to place my then you'll think about it. Then you think about it. So the cost we incur as a rent that we give for the people to position or to station our transmission towers is called right of way cost. Right of way. Higher is the transmission voltage, more is the ROW costs. So all these costs will increase as we increase the transmission voltage. Okay. So these are the disadvantages. These are the disadvantages. Okay. Any doubt in this disadvantages, ma? So one thing you remember, insulation voltage is always provided between the phase to neutral voltage. Why? Because suppose this is one more transmission conductor. So this voltage is between this conductor and this conductor. This voltage is line to line voltage. Okay, line to line voltage. And moreover, providing insulation for phase to neutral voltage is cheaper when compared to the providing insulation to line voltage, because it will directly reduce by a factor root 3 voltage. So insulation is provided for phase to neutral voltage. Understand? So now there are advantages, there are disadvantages. So now what is the optimum choice of transmission voltage? What factors govern that what should be our ideal voltage for transmission? Okay. Factors that govern the transmission voltage are, the first is length of transmission line, actual word is distance over which power is to be transmitted. Okay. The second factor is the quantity of power that is to be transmitted. So depending upon the distance and the quantity of power that you want to transmit, you will decide the transmission voltage. You will decide the transmission voltage. Okay. And the second, one more important point is if you plot the curve between cost of transmission line on y-axis, transmission voltage on x-axis, then this curve, it will vary in this fashion. So initially it will reduce and it will reach a minimum point and then again it will increase. This is called optimum voltage of transmission. Cost of transmission line, AC transmission line. AC transmission voltage. because of beyond 500 kilometers nowadays, we go for HVDC transmission lines. So remember, beyond 500 kilometer HVDC transmission line is preferred. Okay. So one of the empirical formula that we use to arrive at this optimum voltage is V optimum is given by 5.5 into square root of 0.62 L plus P divided by 100. So many kilovolt RMS, where L is the length of transmission line in kilometer and P is the three-phase power to be transmitted in kilowatt. So just to arrive at the optimum voltage, some empirical formula that you can apply is 5.5 multiplied by square root of 0.62 into length plus P divided by 100, where L is the length of transmission line in kilometer and P is the three-phase power to be transmitted in kilowatt. Okay. So the factors that govern are the what is the length and how much power you want to transmit. Okay. So we'll take just a random example and try to understand the formula. Say, for example, you want to transmit 400 megawatt of power over a distance of 300 kilometers. Then compute the optimum voltage of transmission. So how I have to apply the formula? So the optimum transmission voltage is 5.5 into square root of 0.62 multiplied by 300 kilometers the length plus 400 into 10 cube, because here we have to substitute the power in kilowatt. 400 megawatt means 400 into 10 cube kilowatt divided by 100. You calculate this value and tell. Anyone, what is the value?
355.85.
350
355.85
kilovolt. Okay. So we cannot design the voltage for 355 k. So suppose you are given two choices. That means you have a 220 kV line. The next choice is 400 kV line. Okay. So now this value falls in this bracket because the insulators, transmission towers, conductors are already pre-designed for these voltages, 220 kV and 400 kV. Now you calculate the cost of transmission line for 220 kV. Let us say it is 500 crore, and for 400 kV it is coming around 430 crores for the same power transmission and same distance. Then the obvious choice will be again based on the cost. So we go for 400 kV transmission line. That is how the choice is being made. Okay. Esma, is this concept clear? So it gives a rough estimate of optimum voltage. Then the standard voltages will compare and then make a cost effective choice. Okay. The next is the levels of voltage in India. So what is the lowest voltage that you can that you see in the power system network? 230 volt phase to neutral RMS voltage. That is the least voltage that we see in our Indian electric power network, where you will see in our domestic households. The, the next voltage is 415 volt line to line RMS voltage. This we will see in the low voltage distribution networks. Next to highest voltage is 11 kV line to line RMS voltage. Okay. Next is 33 kV line to line RMS voltage. Next is 66 kV line to line RMS voltage. Now, these two voltages, that is 230, they are called low voltage. According to IEEE, any voltage less than 1000 volts is low voltage. Any voltage less than 1000 volt is low voltage. Now these voltages, these three voltages are classified as high voltages. High voltages. Understand? The next level of voltage that we encounter in our power system network are 132 kV. All our voltages line to line RMS voltages. 230 kV. Okay. And next is 400 kV. Next is 765 kV. Okay. Line to line RMS voltages. Okay. These voltages are called extra high voltages. Extra high voltage levels. Whereas 400 levels is called modern extra high voltage. And 765 kV and above are called ultra high voltages. Ultra high voltages. In the world, the highest voltage of transmission is 1100 kV. I think India also some texting of 1100 kV line is going on. You can search in Google. Probably they have not commissioned. They are in the still in the testing phase. So the in the world, highest voltage of transmission is 1100 kV, whereas in India, I guess it is 765 kV still. But again, Google and correct it. Okay. So these are the different voltage levels and their classification. What is a low voltage? What is a high voltage? What is extra high voltage? Modern AHV and ultra high voltages. Okay. Let us take break for 5 minutes, drink water, and we'll continue the session. Okay. Thank you. Hello, welcome back. Yeah. So we'll move to the next topic. We'll define two types of transmission lines. As I said, any conductor that carries power from one point to another point is a transmission line. It can be a very small cable carrying the power from your room switchboard to your fan or to your AC. It is also a transmission line. Now, these transmission lines are again classified into two terms. One is feeder, the other one is a distributor. What is a feeder? Feeder is an electrical conductor which is not tapped in between for power. That means there is a sending end point and receiving end point. In between these 2 points, nowhere no tapping is done to tap the power from it. Okay. So current in the feeder remains constant. So in a distribution system, feeder connects a substation to the area where power is to be distributed. So remember, feeder is a transmission conductor which is not tapped in between. So so what is constant in the feeder? Current in the feeder is constant. Next. The main consideration for designing the feeder is the current carrying capacity. Depending upon how much current we are carrying, it is the main criteria that decides the design of the feeder. Since the current is constant in feeder, it has constant current density. Okay. So in a feeder, current, in fact, the current density is constant. So many times the question will come, on what factor the design of feeder is governed? Either you should say, if the option is current carrying capacity, you have to put it. Otherwise, you have to put current density. Okay. Next, distributor. A distributor is an electrical conductor or a transmission line where tappings are made. Tappings are made at many locations in order to draw the power. Understand? So if you look at the transmission line that is going in front of your house in your street, you will be drawing power from it. Your opposite household person will be drawing. Your adjacent household person will be drawing. So tappings are provided for such a transmission line at various locations. Such a transmission line is termed as distributor. So a distributor is a transmission line or electrical conductor from which the tappings are taken for the supply to the consumers at numerous locations. So since the tappings are provided at numerous locations, the current through the distributor is not constant because tappings are taken at various places along its length. The main consideration in designing the distributor is the voltage drop. That means distributor should be designed to to minimize the voltage drop. Why? Because all customers should get proper voltage. So at the sending end of a distributor, usually the customer will get high voltage. At the far end of the distributor, the customer will get low voltage. So however, we have to design the distributor in such a way that the overall voltage drop in the distributor is minimum, so that every customer who is connected, who is tapping power from the distributor, will get proper voltage profile. So the size and length of a distributor should be such that the voltage at the consumer's terminals is within the permissible limits, that is plus or minus 6% of the rated value. Okay. So feeder is not tapped in between, distributor is tapped everywhere. Current is constant in feeder and current is continuously changing in distributor. Okay. So the main design criteria of the feeder is the current density. The main design criteria of the distributor is the voltage drop. Understand? So what is the criteria for selecting the insulation level of a transmission line? For transmission voltages beyond 220 kV, the insulation is divided by the operating voltage of the conductor. As I told, we have to design the insulation based on the phase to neutral voltage. So for transmission lines below 220 kV, insulation is decided by the operating voltage of the conductor. That means voltage of the transmission line. For voltages beyond 220 kV, the insulation design is governed by switching over voltages. Switching over voltages. Why? Switching switching off circuit breakers will create very high voltage transients which may damage insulation. So, so switching severity increases as the voltage that we are switching increase. Suppose if you are closing a switch in your household, you are making or breaking 230 volt. Understand? Whereas if you make break 1000 volts, then the arc severity of arc restriking voltage, everything will be very high. Understand? So as the voltage keeps on increasing, the switching transients are more and more dangerous. So for voltages beyond 220 kV, the main design criteria for insulation is they should be able to withstand this high voltage switching transients. Okay, but these switching transients are less severe below voltage of 220 kV. Okay, so for below 220 kV, insulation is governed by operating voltage, and for 220 for beyond 220 kV, the insulation is governed by switching over voltages. Switching over voltages. Many times a gate or IES objective question. The main criteria for selecting selection of the conductor size. Who decides the conductor size? For voltages below 220 kV, conductor size is decided by the current carrying capacity or current density of the conductor. How much current is passed through the conductor? That is the main criteria for selecting the size of conductor. For up to which voltages? Up to 220 kV. Up to 220 kV. Okay. For voltages beyond 220 kV, the conductor size is decided based on the electric field intensity surrounding the conductor surface. Electric field intensity at the surface of conductor, this is called as corona. So beyond 220 kV, the size of the conductor is decided by corona factor. Corona factor. These are very important points. Okay. Amma, any doubts in this one? In these 4 points, you're having any doubts? Okay. Now next topic is types of conductors. So there are solid conductors and stranded conductors. So solid conductors are, you can see in the image, this is a solid conductor. Let me put another marker. This is solid conductor, whereas this is a stranded conductor. Solid conductors are constructed of one single piece of metal. It is tougher than a stranded conductor. It is having more mechanical strength. It is tougher than a stranded conductor. Okay. Whereas stranded conductors are formed by, how they are formed? The material is divided into thin strands, and these strands are spiraled in opposite direction so that they get the binding effect. Okay. So this binding effect will give you what? It gives you, so here what they do is, metal is made into thin strands. I don't know what you call strands in Kerala. Strands, and these strands are spiraled in opposite direction to get binding effect. Binding effect. Okay. So what is the disadvantage of solid conductor? It is solid conductor has no flexibility. We cannot bend the solid conductor. Solid conductor, it is very difficult to string between two towers. So this is one tower and this is say one more tower. So now it is very difficult for solid conductor to string or to hang between these two because it does not offer any flexibility, and there is a chance that because of the tension this may get break. It will break at this point. Okay, so solid conductors are very difficult to hang. So when you go for stranded conductors, they are having more flexibility. They are having more flexibility that they can be easily bent. So stranded conductors are easy to bend and they can be easily hung between the two towers. Understand? So again, types of stranded conductors is AAC. AAC means all aluminum conductor. All aluminum conductor. That means all the strands are made up of aluminum only. Then it's called AAC. So all the strands are of aluminum with 99.7% purity. 99.7% purity. This aluminum conduct all AACs are widely used in coastal belts where the corrosion is more. Where the corrosion is more. So they are highly resistant to corrosion. They're mainly used in coastal areas where the moisture in air is more. Moisture in air is more. So low tensile strength because aluminum is a lighter material. Aluminum is a lighter material which is having lesser density. So they don't have the sufficient mechanical strength. Since they are not having sufficient mechanical length, they permit low span. They permit low span. Sir, what is span? Span is nothing but this distance from one tower to the other tower. This is the span. Whereas this distance, that is sag. Okay. Suppose if you keep the vertical line connecting the two transmission conductors to the transmission conductor which is having some bend. So this is called sag. Okay, span is the length between the two towers. It is called span. Since they do not have sufficient mechanical strength, they permit low span length. Okay, so what is the disadvantage here? Less mechanical strength. What is the advantage? Highly anti-corrosive. It is highly anti-corrosive. The most commonly used standard conductor is the ACSR, aluminum conductor steel reinforced. Aluminum conductor steel reinforced. Here, the middle or the center conductors are the made up of steel strands. You can see here. These are all steel strands which I am marking in green, and the most major number of strands, outer strands are made up of aluminum. Okay, so it has a steel core forming the central layers of standard conductors, around which we have layers of aluminum strands. The important advantages of ACSR is it has flexibility as well as tensile strength. Because of the inner steel strands, there is added tensile strength to the conductor. Because only the steel strands are of less quantity, more aluminum strands are there. They are lightweight, small sag. I told what is sag. Smaller support is there, high corona inception level. High corona inception level means the voltage at which corona occurs is high. So because this addition of steel strands will increase overall size of the conductor. If the size of conductor increases, corona reduces. Remember this thumb rule. Size of conductor increases means corona decreases. So the addition of steel strands in between offers more mechanical strength, increases overall size of conductor, with which the two advantages that we get is corona is reduced, and even to some extent skin effect is also reduced. Skin effect also reduced. Okay, this is about the ACSR conductors. This is the most widely used overhead transmission conductor all over across the world. Most widely used overhead transmission conductor. Okay, next few important points is that so in a ACSR conductor, if all the strands are identical, that means they are of same size, then the total number of strands n, capital N, is given by 3x square minus 3x plus 1, and capital D is given by 2x minus 1 into D, where n is the total strands in ACSR conductor and x is the number of layers in ACSR conductor. Okay, where small d is diameter of each strand and capital D is diameter of ACSR conductor on the whole. Okay, so that means if you, yes, suppose if I take one steel conductor, only one steel conductor, and if I surround with identical size aluminum conductors, I can surround with 6. How many layers are there? First layer contains steel strand, one steel strand. The second layer contains 6 aluminum strands. It is X here is how many layers are there? 2. How many number of strands are there? If you substitute in that formula, 3 into 2 square minus 3 into 2 minus 1. Sorry, plus 1. This will give you 7. So the total number of strands in this conductor is how many? 7. Likewise, you can see here in the first image, 2-layer ACSR has 6 aluminum strands and 1 steel strand. And if you go for 3 layers, you will get total number of strands will become, n will become 19. Okay. Similarly, if you go for 4 layer, the total n will become 37. Okay. If you go for 5 layer, it will become, n value will become, actually it should be 54. It is 5 layer, it will go by 54. So like this, if the strands are identical in nature, then you can easily calculate the total number of strands. So x n. So 2 layers, 7. First layer 1, 6. 3, you're going to get 19. 1, 6, 12. 4 layer, you're going to get 37. 1, 6, 12, and 18. 5 layer you're going to get 1, 6, 12, 18, and I think it is 24. So like this, you can compute depending upon the layers, how many strands would be there. And one more important point is when you specify a ACSR conductor by two numbers. Here they're mentioning 54 aluminum and 7 steel strands like that. When I say my ACSR conductor is 7 bar 54, when somebody gives you this data, the lowest number is steel strands. Either it can be right side or left side, it doesn't matter. The lowest number is steel strands, highest number is aluminum strands. The total strands is the sum of these two. So when I say 7 bar 54 ACSR, it is a ACSR conductor containing 61 strands, out of which 7 are steel strands, 54 are aluminum. Or you can even say first two layers are steel and the remaining 3 layers are aluminum, like this. So if someone says uh, 36 bar 1 ACSR, that means what? Lowest number is 1, which is steel strand, number of steel strands, and highest number 36 is the number of aluminum strands. So like this, when the all strands are identical, these definitions and these formulas are applicable. Okay. The other type of conductors apart from the ACSR are the hollow conductors. Hollow conductors. So in hollow conductors, the middle portion of the conductor does not contain any material. Only the outer portion will have the conducting material. Okay. Where their hollow conductors are bus bar is a location where you connect both sources and loads together. Okay, so the highest current will be in the generating station bus bar, where you are generating the huge amount of power at low voltage. So the current that is injected into bus bar is very high. And the second point is, to the same bus bar, you are connecting the generator and you are also connecting the transformer. Okay, see, connection means not a simple. You have to bolt the copper conductors with lugs, bolts, washers, and nut. So the bus bar should have more physical strength, more tensile strength. That is one requirement because all bolts nuts will be connected to that. And the second one is, since they are carrying huge amount of current, the I square R losses will be very high. So in order to cool down the bus bar, some air circulation or oil circulation or some ventilation is required. Some cooling mechanism is to be kept. So in hollow conductors offers, because the inner portion is empty, we can use that portion for circulating air or circulating uh, some sort of insulating oils to cool the bus bar, to cool the bus bars. And since they are solid structures, we cannot have more spans. We cannot have more spans. Only for short lengths, we can use the hollow conductors. We can use the hollow conductors. They can be cylindrical hollow conductors or rectangular hollow conductors or even ACSR. This is a ACSR, sorry, uh, stranded hollow conductor. Stranded hollow conductor. Understand? This is rectangular or different hollow conductors. It's a cylindrical hollow conductor. So hollow conductors are used in bus bars. They can be used only for shorter lengths because they cannot be bent. Their strength is more, and they offer better cooling rate. Why? Because some air circulation will happen in between the in the hollow portion of the conductor, which offers better cooling. Okay, so one more advantage of hollow conductor is skin effect is less. Skin effect is less, and yeah, skin effect is less. Corona effect is also less. Understand? Skin effect is less and corona effect is also less. This is about the hollow conductors. Next, the other types of conductors are expanded ACSR conductors. Expanded ACSR conductors. So in expanded ACSR conductors, what we'll do is we fill the between one layer of strands to the other layer of strands, we fill some garbage insulating materials like paper, waste paper, jute, jute, okay, or some Hessian type of material to intentionally increase the size of conductor. To intentionally increase the size of conductor. In the image, you can see at center steel strands are there, and in between the steel strands and aluminum strands some filler material. These filler materials can be any insulating material like waste paper, jute, paper, jute, Hessian, which has some good insulating properties as a filler material. And again, this filler material, after the filler material, will place the aluminum strands. Okay, so with which we are intentionally increasing the size of conductor. As I said earlier, increasing the size of conductor will have certain advantages that we'll discuss in the coming classes, which reduces the corona loss is one of the advantage. And second advantage is inductance per phase of conductor also reduces. How we will discuss in the next class. Okay, so these are called expanded ACSR conductors. The last type of conductors which are commonly used for high voltage or EHV lines and above, extra high voltage lines and above, we commonly use bundled conductors. We commonly use bundled conductors. They are nothing but the individual ACSR conductors are joined by metallic links. Individual ACSR conductors are joined by metallic links. See, here it is a metallic link. Here it is a metallic link which is joining two ACSR conductors. So it is a bundled conductors of two subconductors. So these are, which ink will write, I don't know. Yellow, black, yeah. This is one subconductor. This is one subconductor. Okay, two subconductors are joined by metallic link to form a bundled conductor. The other name for bundled conductor is composite conductors. The other name for bundled conductors, synonymous name is composite conductors. Okay, here in this second image you can see three individual ACSR conductors are coupled by three metallic links to form a bundle of three. Bundle of three conductors. Okay, understand? So now overall, with the interconnection with the metallic links, the overall effective size of the conductor, there is something called as geometric mean radius, GMR. We'll discuss in the next class. Geometric mean radius of the conductor increases. So geometric mean overall effective radius of the conductor will increase, which drastically reduces the corona effect, So this is the, again, it is a bundle of how many conductors here? Bundle of four. Bundle of four conductors, four subconductors. Okay, so bundled conductors are used in transmission lines where voltage exceeds 230 kV, that is extra high voltage and above. At such high voltages, ordinary conductors will result in excessive corona and noise which may affect the communication lines. One of the disadvantages of corona is the communication interference. Communication interference. All the wireless signals that are being transmitted will be severely affected because of the corona, and it will give some power loss also. We'll discuss what are the disadvantages of corona in corona chapter. The increased corona will result in significant power loss. Power loss is one disadvantage. Communication interference is one disadvantage. Bundled conductor consists of 3 or 4 conductors for each phase. Gentlemen, it is every phase conductor is a bundle. That means R phase will have such bundle, Y phase will have such bundle, B phase will have such bundle. In the next image, I will show. Okay. So bundled conductor consists of 3 or 4 conductors for each phase. The conductors are separated from each other by means of spacers at regular intervals. Thus, they do not touch each other. They are called spacers or metallic links. Okay. Why bundled conductors are used? Many times a GATE and IES question, to reduce corona effect. That is the main advantage. So you can see a double circuit transmission line with bundled conductors. Double circuit transmission line with bundled conductors. Okay. So every phase conductor is bundle of, here I think it is 5 conductors. You can only see 3, but it's a actually 5 conductor bundle. Okay. Amma, have understood the type of conductors? Any doubts in this section? So let us discuss skin effect and close for today. So next topic is transmission line parameters. So there are 4 transmission line parameters, 2 series parameters and 2 shunt parameters. So this is the conductor phase and this is the ground or neutral. So for any transmission conductor, there are 4 parameters: series resistance, series inductance, shunt conductance, and shunt capacitance. So 2 parameters are present in series, that are resistance and inductance. 2 parameters are between the conductor and the ground. They are conductance and the capacitance. Okay. 2 series parameters and 2 shunt parameters. Okay. So what is the time constant of an RL circuit? Series time constant of transmission line is given by L by R. The shunt time constant is given by C by G. C by G. So if, I'll write in white, if series time constant of a transmission line is equal to shunt time constant, that is if L by R of a transmission line is equal to C by G, then it is called distortionless transmission line. It is called distortionless transmission line. So the series time constant is given by L by R. The shunt time constant is given by C by G. If both these values are same, then it is called distortion transmission line. There is no distortion of the waveforms that are being transmitted in this transmission line. Remember this condition. Okay. Now, if you see any conductor, the resistance, the DC resistance is given by R is equals to, what is the formula? DC resistance is given by rho L by pi R square. So many ohms. What is rho? resistivity of conductor material. Okay. Next, L is the length of, here in directly we can write transmission line or conductor, and pi r square is the area of cross section, or we can, in layman's language, you can say size of conductor. Okay. So DC resistance is given by rho L by pi r square, so many ohm. Resistivity of the conductor material, length of the line, and pi r square, area of cross section or size of the conductor. Okay. So, what is skin effect is that when a conductor is carrying a steady DC current, this current is uniformly distributed across the entire cross section. However, when the same conductor carries the AC current, the current is concentrated more at the surface of the conductor than the core. This phenomenon is known as skin effect. This phenomenon is known as skin effect. Okay, that means once you pass, now let me write in blue. So this is a conductor, imagine. So once you pass, this is same conductor where I'm applying AC voltage. VDC, VAC, IAC, IDC. Now this total cross section area is used for current conduction and current is uniformly distributed. But when you pass through the same AC conductor, current is more at the surface and it gradually decreases as you move towards the core of the conductor. So here the entire area of cross section of the conductor is used for current conduction, whereas when you pass AC current, that is not the case. That is not the case. So here, if the total uh, area is say A is the area used for current conduction. Here A dash is the area used for current conduction. Then R, we know that A is greater than A dash because in DC the complete area is used for current conduction, whereas in AC only the some portion of the conductor is used for current conduction. So RDC, that is equals to rho L by A, is less than RAC, which is rho L by A dash. Why? Since uh, A is greater than A dash. So RAC is greater than RDC, or we can approximately write RAC is 1.6 times RDC. So when you pass AC current through the, when you pass DC current and AC current through the same conductor, the resistance offered to AC currents is greater than the resistance offered to DC current, because the current concentration is non-uniform in AC conductors, whereas the current concentration is uniform in the DC conductors. This is due to this effect is called skin effect. This effect is called skin effect. Why the skin effect comes? Because of the inductance parameter. Because of the inductance parameter that comes into picture when you pass AC current. Because of the inductance parameter of the conductor, which comes into picture when you pass the alternating current. Okay, for DC currents, there is no inductance phenomenon. Inductance parameter does not come into picture when you pass DC current. How and why we will discuss in the next class in detail. What is that inductance parameter? Why it will only come for alternating currents? Why it is absent for DC currents, and all the details we'll discuss in the coming class. Okay. Thank you. That's it for today. Any doubts you can ask. Otherwise, you can leave the session.